institution here, but you notice that on various walls there are video screens showing a kind of greatest hits clip show. You get to see David Attenborough and others with animals doing fiercely clever things right here at this desk, and others are doing demonstrations with extremes of high and low temperature, or a Rube Goldberg machine with the marble running down. And I'm watching this before my own lecture, and I'm thinking, those poor audience members forced to sit through all this mummery when what they really want are some good old equations. You have come to the right lecture. We all know the importance of equations in physics, and we also know that they're treated as kind of scary. You're not supposed to tell people about them. Stephen Hawking says every equation cuts your book sales in half. My publisher didn't like that idea, but there's also a level of appreciation and understanding you get when faced with a good equation. Here is a famous equation. This is an equation that we all know was given to us by Albert Einstein. E equals mc squared. The energy of an object just sitting there is equal to the mass of the object times the speed of light squared. It's almost an icon of inscrutability, but it's actually not that hard to understand. It's, a little multiplication. There is a superscript exponent for the 2, but that's okay. We know how to square a number. It's not really that hard. It's also not what physicists think of when they say the phrase Einstein's equation. Here is Einstein's equation, as physicists think about it. This equation is the dynamical equation telling us how the curvature of space-time responds to energy and mass and momentum in the universe. If you were to say it out loud, r mu nu minus 1/2 r g mu nu equals 8 pi g t mu nu. We never show you this equation. You don't see this one for obvious reasons. It seems very intimidating, doesn't it? There's all these symbols. Some of them are big, some of them are small, some of them are Greek. And it seems like it would be an effort to explain it to people. But I'm trying to imagine that maybe the effort is a little bit worth it, at least at some level. An equation is often related to a poem in some sense. And it's actually very similar. Equations are short, and they are powerful, and they are precise. Every little bit counts. Every little notation, every little dash, etc., means something. And it is a little bit of work to dig into what those symbols mean, but it's very doable work. We have 58 minutes left. We're going to do it. And I think it's worth doing it because, I'm not going to give you homework unless you really want some. I have good homework available, but the point is that if you understand the equation, you appreciate the science at another level that you wouldn't otherwise do. So it's worth the effort to at least think about it. What I'm hiding from you is that it's also kind of fun. I think that it's not just a matter of effort. You'll see this and you'll say, why did they always hide it from me for all those years? So we'll start gradually, okay, with the idea of classical mechanics. Sir Isaac Newton, a famous English person, gave us classical mechanics in the 17th century, and it really boils down at the end of the day to a single equation, F equals ma. There is a little bit of intimidating factor here because the F and the A have little arrows over them. That's because they are vectors. What this equation means is that the force that acts on an object is proportional to its acceleration, how fast it starts moving, the rate at which it starts moving, and the constant proportionality is, once again, its mass, m. Force equals mass times acceleration. This seems straightforward enough. It was a big deal at the time because it used to be thought that nothing could move at a constant velocity forever unless you kept pushing it. And Newton comes along and says, no, if you don't push something, that's exactly when things move at a constant velocity. It's friction and so forth that slow them down. So what is so great about this equation? Why is it such a big deal? Well, it's both precise and it's everywhere. By precise, we mean it's not just a suggestion.
Asthma doesn't want you to be the cool mom. Triggers can pop up at any moment, and asthma says you can't. but by making better control of your severe asthma possible. Tespire says you can. Tespire is an add-on treatment for people 12 and over that treats your type of severe asthma to help you prevent attacks, breathe better, and relieve your asthma symptoms. Tespire is not a rescue medication. Serious allergic reactions may occur. Get help for swelling of your face, mouth, tongue, trouble breathing. Rash or eye allergy can happen. Don't stop asthma treatments without talking to your doctor. Tell your doctor if you have a parasitic infection or your asthma worsens. Avoid live vaccines. Sore throat, joint, back pain may occur. By helping control your asthma, Tespire lets you be you. Ask your asthma specialist for Tespire by name.
You do realize this doesn't open till next year, right?
Hey, I'm Mike. I'm Dylan, and we're the Ride Guys. And today we are riding Stardust Racers at the brand new Universal Epic Universe. Oh, we have been waiting for this day ever since we did that special first look episode.
You know, finally, I'm out of snacks.
So if you're ready,
We're ready.
let's ride. Shaboom!
Coming for the crown, it's a shutdown. We're here in Celestial Park, one of 5 amazing worlds at Universal Epic Universe. Universal Orlando's newest theme park is amazing, and we're going to show you some of that amazing today.
So let's get to your questions. What kind of ride is this? It is the most thrilling coaster in the entire park, but more on that soon.
Does this ride have a backstory? Dylan, my friend, it's time for the first ever dream sequence in Universal Epic Universe.
Epic boom.
Attention, Celestians! You've learned through the power of the cosmos to capture the comets that shoot through the stars above and ride them!
Yes, residents of Celestial Park, because of you, explorers to your beautiful world can now race on these comets into the furthest reaches of the cosmos to see whose comet is the fastest. How fast does it go? Fast. Max speed is 62.6 miles per hour, making this the fastest, most intense coaster in all of Universal Epic Universe, with the tallest point being 133 feet.
What should I look for in the cube? Comets. You're going to journey through all of these comets that have crashed into the ground, still glowing from within.
What's better, riding day or night? They're both awesome, but here's a fun fact. There's no external track lighting at night, so the fully illuminated ride vehicle actually looked like comets shooting through the night sky.
That was fun.
Tell me about the barrel roll. You've done your homework. Stardust Racers features the Celestial Spin. This is a signature barrel roll where the ride vehicles travel under and over each other into an inverted crisscross, and yes, it's as awesome as it sounds.
How tall do I need to be to ride? Height requirement is 48 inches.
Who will like this ride? Thrill seekers, roller coaster enthusiasts, this race coaster is for you.
All right, speed round time. Child swap, yes. Universal Express Pass, yes. Early park admission, yes. First launch, 4 Gs. Lockers, you'll need one. I'll need one.
Well, we have to talk about this. Stardust Racers is a dual launch coaster where it has 2 ride vehicles racing at the same time on 2 separate tracks.
Dibs on yellow.
Dibs on green.
Woo! This is a race, so I'm gonna beat Dylan. That's the goal.
Oh, it's going faster than I thought. All right.
Are you ready for the launch? Are you ready for the second? That's so high! Whoa! We're going this way! Whoa! Oh! Hey, Dylan! Okay, he's in the lead. We gotta catch up. That's the way to do it! Woo-hoo-hoo! Whoa! I did it!
Awesome.
So awesome. We have to do it again right now.
Man, we've done like 25 of these. You know we got to do the outro first, right?
Okay, fine, but I'm gonna do it fast, all right? Like, subscribe, comment below on how much you love Stardust Racers and what ride at Universal Epic Universe you want us to do next. Hey, Dylan!
Shaboom!
Shaboom! Coming for the crown, it's a shutdown. Day night. Nope. Dylan, can you clap? Oh. Look at this. This is nice. A little chillier than I thought it would be. Hit it again. Oh. Oh, do it again. All right. Nighttime is the right time. Do it again. Nighttime is the right time. Do it again. Nighttime is the right time.
Right? It's not saying, well, you know, the more you push, the faster things go. That's true so far as it goes. But this is numerical and quantitative and precise. And if you want to fly a rocket to the moon, you're going to need to know exactly how much fuel you need. This kind of equation takes that into consideration. But the everywhereness is even more important. This equation doesn't say that one time that I pushed my car, I acted a force on it and it accelerated a little bit. It says every time anybody in the history of the universe pushes a car or anything else, the force that they exert on it will be proportional to the acceleration. That's really why the equations are so great, because they give you, even though you're just sitting here thinking about it in this room right now, suddenly you have an insight into the workings of the whole entire universe throughout its entire history, if things go well. That's why it's worth kind of contemplating what's going on here. It also doesn't tell you anything until you tell me what the force is. How much force am I putting on things? Well, here's another famous equation, also from Sir Isaac. The story of him sitting under the tree and having the apple fall on his head is probably apocryphal and certainly was promulgated by Newton himself, who thought it kind of burnished his reputation a little bit as an inscrutable genius. When the apple fell from the tree, the point is not that Newton discovered gravity. Guess what? Even before Newton, we knew that there was something called gravity. What Newton realized is that universality, that everywhereness of gravity. The fact that his inspiration was that the apple falling from the tree is explained by the same set of rules that explains the planets moving around the sun, etc. The rules apply everywhere. And in this case, the rule is that the force due to gravity is inversely proportional to the distance between two objects. So if we have a heavy object, capital M, light object, little m, we make another little vector called E, which is just the directionality of where the force is pointing. It goes from little thing to big thing. And the force is the mass of the big object times the mass of the little object divided by the distance between them squared times a constant, capital G, which we call Newton's constant for obvious reasons. And this pair of equations, F equals ma and F equals gmm over r squared times the unit vector, they make the universe go, or at least we thought they made the universe go until Professor Einstein came.
Engineered for superior support, Sealy Posturepedic was built to be the best for lasting comfort where you need it most. All night, every night. Shop Sealy Posturepedic today at Raymore and Flanagan. Convenient financing plans allow you to buy now and pay over time. Plus, receive free next-day mattress delivery and removal.
With Geico, we can easily bundle home and car insurance and save even more.
Yeah, just like that breakfast burrito.
There isn't too much hot sauce, is there? I have a sensitive palate.
I actually like hot sauce.
How about guacamole?
I don't really know what we're talking about anymore.
Burritos.
Insurance.
Get more with Geico.
Came along, they did a pretty good job. If you want to get a rocket to the moon, you don't need to know about Einstein's equation. You definitely need to know about Newton's. And already, well before Einstein, there's a really important implication of this, which is going to be important later on in the talk, but it's also showing you some of the power of thinking in terms of equations. Because if the force that you act on something is the mass times acceleration, and the force acting on something is the mass of the other thing acting on it times Newton's constant times its own mass divided by r squared, then the masses cancel out. You can divide by little m. There, we just did some math. Pause to congratulate ourselves for doing some math. We divided by little m on both sides. And you instantly learn something profound and counterintuitive about nature. The acceleration due to gravity that acts on an object doesn't care how heavy that object is. This seems counterintuitive. If I take a hammer and a feather and I drop them, they will drop at different rates. And in my brain, I think that's because the hammer is heavier. So here is an artist's impression of an experiment that was actually done by the Apollo astronauts. They took a hammer and a feather up there, they dropped it. They had very bad video cameras for some reason, so this is a painting remembering the event, but the point is, on the moon, the hammer and the feather fall at the same rate. The real reason the hammer and the feather on Earth do not fall at the same rate is because of air resistance, clearly. But this is a crucially important insight into how gravity works. Because again, it's everywhere, it's universal. All objects accelerate under the same way, the same rate, under the force of gravity. Gravity is a universal force. Keep that in mind. It's going to be on the test. It's going to be coming up later. And for centuries, classical mechanics was so successful that people thought they had figured out the basic framework according to which the universe works. And it was just a matter of getting, all right, what are the forces? What are the things acting? We'll put it into this framework that we have. But then the 20th century comes along. Quantum mechanics, that will be book 2, by the way. So I'll be back here to be talking about quantum mechanics later. But the other thing that happened is relativity. And relativity came in 2 pieces. One is special relativity in 1905. It's good occasionally in science talks to see photographs of Albert Einstein when he was young, when he was thinking up all this stuff. He kind of went to seed later on. He looks avuncular. Here, he looks like the smartest guy in the world. He looks smarter than you, right? Like you would talk to him and you would feel intimidated. Someone was combing his hair. And special relativity, there's a list of things going on about the speed of light and time dilation. It's all wonderful. We're not going to get into it. The book gets into it. Read the book, but we don't have time for that right now. What I want to do is simply use it as a springboard to general relativity. General relativity was where Einstein really became a celebrity. In a very real sense, special relativity was Einstein was at the right place at the right time, and he put a sort of capstone, put things together that other people had already been working on. General relativity was his baby, but he kind of got there reluctantly, because this is 1905 special relativity. In 1907, Hermann Minkowski, who had been Einstein's math professor, says, your math professors read your famous scientific papers, and Minkowski said, I have a better way of thinking about this. When you talk about special relativity and time dilation and all that stuff, it's more mathematically elegant to imagine that what's going on really is that you have unified space and time. And he has a quote, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. They made very poetic scientists back in those days. People were, skeptical, actually. They were not immediately impressed. One person who was skeptical, Albert Einstein. He says to his old professor, Minkowski's formulation makes rather great demands on the reader in its mathematical aspects. So if you're ever reading something and you're like, the math is too hard here, imagine that you're Einstein and you think, the math is too hard here, I'm not going to bother. As good as Einstein was, in fact, I would argue that in some sense he's underrated as a physicist, but he was a physicist at heart. He was not a mathematician. He didn't love math for its own sake. He learned exactly as much math as he needed to know, and no more than that. So he looks at Minkowski's work and he says, okay, you're doing some formalism, it's all very elegant. It doesn't really do me any good. I'm a down-to-earth kind of guy. I want to imagine people going to the speed of light, things like that. But why did Minkowski think this? Because guess what? Einstein was totally wrong, and he's going to change his mind very quickly. It's the geometry of space-time that really makes it an interesting thing to think about, rather than space and time separately. Think about what we mean by the geometry of space. There's a lot going on in the geometry of space. We're imagining here good old Euclidean geometry, the geometry of the tabletop. And it's useful to us. For example, if you have coordinates, if you have an X and Y coordinate system on the tabletop or on the city or whatever, you can use that to figure out how far you've gone. This is a typical geometry problem. You can invoke Pythagoras' theorem, right? If you're moving on a straight line, but it's diagonal compared to the x-axis and y-axis, the distance you travel is going to be the square root of x squared plus y squared, okay? The hypotenuse squared is the other two sides squared, their sum.
I'd do anything.
Let's put magic fairy dust on Murphy and Buzz so we can play together forever.
Wait, I have a better idea. Let's go to PetSmart. Check out Hill Science Diet. It's formulated for long, healthier lives. Nice. PetSmart. Anything for pets.
That's something that you might use when you have, the guy is supposed to have a little odometer here, counting his steps, figuring out how far he's gone. So it's a practical, kind of down-to-earth thing. What Minkowski says is that you can think about Einstein's special relativity as exactly the same kind of thing, but replace distance traveled with time elapsed. So before Einstein and Minkowski come along, time was this universal thing, according to Newton. Everyone agrees on what time is. Not everyone agrees on the distance you travel. That depends on the path you take, right? Between 2 points, you can go in a straight line, you can go in curvy lines, different distances. But time you thought was universal. Minkowski says no. What you have to do is use Pythagoras' theorem for space-time, which involves a little trick, namely a minus sign. So Minkowski says that the elapsed time between two events in space-time can also be calculated in terms of a coordinate system, but now your coordinates are x, y, z on space and t in the time direction. And there's a difference between t, the universal time coordinate on all of the world, versus tau, what we call the proper time, what you actually experience, what you actually measure on your wristwatch. And there's a formula for it, and it looks very much like Pythagoras' theorem, but not quite. Pythagoras says d squared is x squared plus y squared. Minkowski says the time you measure squared is t squared minus x squared. If you've ever tried to wonder which twin it was that aged more in the twin paradox, because I know I've had to wonder, just remember this equation. The minus sign means the more you travel in space, the less time you are going to feel elapsing. That is a brilliant codification of all of the ideas of special relativity right there. So, meanwhile, while Minkowski was saying all these mathematical niceties, Einstein was worried about gravity. When we talked about classical mechanics, the first thing we did is say, okay, let's imagine a specific force of nature, gravity. It all worked out very nicely in the Principia Mathematica. Newton told us both the rules of classical mechanics and his inverse square law for gravity. So Einstein very naturally figured he had special relativity replacing classical mechanics. Now he needs to replace Newtonian gravity. It didn't work. There's sort of an obvious set of guesses you go through as a theoretical physicist. None of them work. You need to come up with something a little more profound. So Einstein hit on something called the principle of equivalence. Remember, even Newton had figured out that gravity is a universal force. Drop two things, they will fall at the same rate, no matter what their mass is, but also no matter what they're made of, no matter what time of day it is, and so on. So Einstein puts this into thought experiment form. He was the best thought experimenter in history. And he says, what this means is, in some way, gravity isn't really a force at all. Because I can't tell if I'm in a gravitational field. I can sit here and I can do experiments. I can drop things and they will fall, and I will say, aha, gravity made something fall. But he says, I would say exactly the same thing if the Earth had disappeared and this whole lecture hall was in a rocket ship, accelerating upward at 1g. That hasn't happened. Do not be alarmed. But Einstein says there's no experiment you can do as long as we're locked in the lecture hall that would tell the difference. Gravity and acceleration are indistinguishable from each other. Now you and I, that's the principle of equivalence, and you and I would say, aren't we clever for having thought of that equivalence? And then we move on with our lives. But Einstein was Einstein, and he's like, this means something. I got to be able to use this to come up with the right way to marry relativity and gravity. And he suspected that what he needed was more math. And he wasn't very good at math, like I said. I mean, he was good at it when he needed to be. He didn't do it for his spare time, though. Happily, one of his friends from graduate school, Marcel Grossmann, was an expert in what at that time was the fanciest mathematics and geometry out there. Here's Grossmann on the left. And so Einstein says, Marcel, you got to help me with this. And Marcel Grossmann taught Einstein what at that time was the most modern ideas in geometry. So what does that mean? What counts as a modern idea in geometry? Well, Euclidean geometry, which we talked about with Pythagoras' theorem, is based, as you might know, on a set of axioms, and the famously weird axiom is the parallel postulate. The idea that if you start with a little line segment, take two perpendicular rays and let them move off to infinity, Euclid says they will stay exactly parallel at the same distance forever. For many years, for literally centuries, millennia, I suppose, people tried to prove this feature of geometry based on Euclid's other axioms. When I was in high school, our geometry teacher gave this to us as an extra credit assignment to prove the parallel postulate. He was very cruel because you cannot prove the parallel postulate, as they realized in the 1830s, because you can.
Febreze. Love your plugins but wish you had more scent control? Meet the Febreze Plug Scent Booster. Enjoy the same 50 days of continuous scent as Febreze Plug, including a cord for flexible placement options and a boost button for extra scent. Febreze Plug Scent Booster.
Replace it with other perfectly good postulates. You can say either that those initially parallel lines converge at a constant rate, or maybe they diverge at a constant rate, and you get perfectly good theories of geometry, different than Euclidean geometry, but perfectly good in their own right. If the lines start to converge at a constant rate, you get spherical or positively curved geometry. If they diverge at a constant rate, you get a saddle or hyperbolic or negatively curved geometry. And these were investigated, and they were just as good as Euclidean geometry. So people started to say, well, why does Euclidean geometry work so well in the world? What's going on? Other people said, we're still making an assumption here. The assumption we're making is that if those lines start to converge or to diverge, they do so at a constant rate. It was Gauss, Carl Friedrich Gauss, one of the greatest mathematicians in history, who said, look, once you tell me that I can have a sphere or a saddle or a potato chip, I can have any wild thing that I want. I could even have a 3-dimensional space or a 4-dimensional or a 29-dimensional space. And they could be diverging some places, these lines, and converging other places, like there's suddenly an infinite number of geometries that I could think about. Happily for Gauss, he had a very talented graduate student, Bernhard Riemann. And Riemann was already a well-known mathematician, but in the German system, there's a never-ending series of exams you have to pass before you can become a professor. And so the last one, the habilitation exam, Riemann gave Gauss a list of possible topics that he could study, and Gauss pointed to the one that Riemann thought was the most boring, the foundations of geometry. Do that one. And Riemann goes off, and it's hilarious to read this. I did this, for writing the book. For the first time, I actually looked at Riemann's paper, and he can't stop kvetching within the paper. He's like, I don't like doing this, but, I'm told to do this. It's not my natural métier. Riemann's purpose was to figure out how to, in absolute perfect generality, capture the geometric structures of a space in any number of dimensions without embedding it in any other space, just its own intrinsic character. So that's obviously, there's a lot of ways that space could curve or twist or bend or whatever. What is the simplest way to distill that down to some usable information? And Riemann, because he was quite clever, he figured out that if you know the length of every curve that you can draw, so imagine on this tabletop you just draw every single curve, both straight lines and curved lines and everything. If you had the information in your brain about the length of every curve that would completely fix the geometry of the space. The only way that those curves can fit together is if the space is flat. Or in this picture, these are spheres with little balls of yarn, little lines crossing on them. Riemann's insight is that all you need to know is the length of every possible curve that fixes the geometry of the space. And how does it work? It's kind of like Pythagoras' theorem again, but because things are arbitrarily twisty, you zoom in. For those of you who know calculus, this is the traditional calculus trick. When things are curvy and changing, you zoom in, and if you zoom in carefully enough, everything looks straight and flat and constant. So Riemann says, I can take some arbitrary twisty curve, I can zoom in on it, and I can use Pythagoras' theorem. So in this case, this little three-dimensional diagram, the length of a tiny little line segment is x squared plus y squared plus z squared, the square root of that. So Riemann's self-appointed task is, let's generalize this. The nice thing about this picture we drew is that it's actually in flat space. So I've drawn coordinates x, y, z. If the space is not flat, if I'm on a sphere or a torus or something crazy, I might not be able to use such convenient coordinates as x, y, and z. And in fact, what happens is when your coordinates begin to get a little bendy and curved themselves, the formulas begin to look a little bit more elaborate and less intuitive. So this may or may not mean anything to you. This is just for those of you who are familiar with the idea of spherical coordinates. So you have x, y, z, but you could also just say, what is the distance to the point? What is the angle from some line of longitude? Or what is the angle from the North Pole? That gives you spherical coordinates, which are very useful when you have spherical symmetry. And here is the formula for the distance of a little infinitesimal line in terms of r, the distance, theta and phi, those two angles. No information about that particular equation needs to penetrate into your brain other than the equation becomes more complicated when the situation becomes more complicated. So what Riemann needs is, what is the maximal complication? What is the most arbitrary way that we can think about this? You stare at this expression, you ask what is going on, and if you're Riemann anyway, you say, okay, I think what's going on is that I have on the left-hand side some interval. I would like to say some distance, but in space-time it's going to be some time. So we use the word interval to mean either space or time. Some interval squared is on the left-hand side. That's what we inherit from Pythagoras. On the right, we have a sum of terms with all the different coordinates times some number, some quantity, right? So dr squared all by itself, but then the theta squared term has an r squared outside, the phi squared has r squared, like there's a whole bunch of things going on. The general pattern is some number times a coordinate times the other coordinate. So coordinate squared times some number. In other words, in space-time, for example, where you have t, x, y, and z, you're going to have a formula for the interval in space-time, just like Minkowski gave us, but maybe more general. So the interval squared is going to have some number times t squared, plus some number times t times x, plus some number times t times y. If you have 4 dimensions, t, x, y, z, there's going to be 16 terms. 4 times 4 is 16, right? T, tx, ty, tz. You can go through them all at home, or right now, in your head, if you're that good. It quickly becomes unwieldy, right? Too many terms you have to write out, it becomes boring. If there's one thing that mathematicians are very, very good at, it is inventing notation that makes unwieldy but understandable things into very elegant but impenetrable things.
We're back, baby! I know what we're gonna do today. Summer is starting right now. Summer is...
We're gonna bust Phineas and Ferb once and for all!
Are we gonna do this again?
Full throttle, full thrust. Put my pedal to the metal, go and eat my dust. I got a license to bust.
I'd usually charge you for that, but I see you're in a song sequence!
Thank
you! Let freedom ring. Let freedom sing. Let it jump for joy. Let it laugh to the point of bursting. Let it hug tight, tighter,
To the military service members who give us the freedom to live happy, healthy lives, we're proud to raise health to give you the same in return. Northwell. Raise health.
So they do that. They invent something called the metric tensor. And the first step here is to relabel your coordinates. You thought you were happy with t, x, y, z, coordinates on space-time, but someone reminds you, you might want to use spherical coordinates or something more complicated. So rather than t, x, y, z, let's call them x0, x1, x2, x3. Immediately someone says, why did you start numbering with 0? Well, it's because physicists, bless their hearts, like to imagine more or fewer numbers of spatial dimensions, right? Maybe only 2 spatial dimensions, maybe 9 spatial dimensions if you're a string theorist, but we only always have 1 time dimension. So give time the label x0, and all the spatial dimensions are x1, x2, x3, etc. And then the whole shebang, you call it x mu. So mu, the Greek letter mu, is an index. It runs 0, 1, 2, 3. Or if you want, t, x, y, z. Completely equivalent. x0 is time, x1 is x, and so forth. That's where the mu is coming from. Remember the mu? The mu's in the news from Einstein's equation, right on the second slide there? Here's where they come in. They are labels on directions you can move in space-time. T, x, y, z. So it's not really that new and crazy. And then rather than saying some number times t squared plus some number times tx, invent a new notation, g mu nu, and g mu nu is simply the number that gets multiplied by x mu x nu in that equation. So the interval squared in perfect generality is g00 times x0 squared, g01 times x0 x1, and so on. We have not yet achieved perfect inscrutability or compactness, so this is just the sum over all those values the indices take of g mu nu times x nu. That big sigma is another Greek letter. It means you sum over all the different possibilities. So these two expressions are exactly the same thing. This little purple thing, sum over mu and nu, g mu x nu, is just g00 x0 squared plus g0, etc. Okay? Now onto the stage comes Albert Einstein, who, as you might imagine, was doing his homework for Marcel Grossman, trying to teach him geometry, and he goes, this is very tiring, writing all these summation signs. I'm going to invent a new notation in which you write the same thing, but you don't write the summation sign. He was so proud of himself. He literally was telling jokes. He said, I've made a great discovery in mathematics. You don't need to write the summation sign. As long as you have repeated indices, you imagine that we mean you should be summing over them. This is called the Einstein summation convention. Not the most important thing Einstein ever did, but he got a kick out of it. Now we have reached full inscrutability. It's very compact. G mu nu x nu. I'm even leaving out some of the complications because I like you. But this is, you see what's going on. We've taken the question, how do we generalize an arbitrary geometry? Well, you need to know the length of every curve. How do you encode that information? Here's how you encode that information in the values of the components g mu nu. Let's see that at work, okay? So g mu nu is the metric tensor. We've already secretly seen it. When Minkowski told us about space-time, he said that the time interval you measure, tau, is related to the coordinates t, x, y, z by tau equals t squared minus x squared minus y squared minus z squared. In terms of that little formula we had on the previous slide, that means that g mu nu is usually 0, right? There's no term in the equation that is x times y, for example. That's why you get all the zeros on the right here. But in principle, the rest of them you can read off. The g00 or gtt is plus 1. gxx or g11 is minus 1, and so on. And furthermore, all of these symbols have meaning. I mean, you knew that they did, but we can even tell you what the meaning is. The spatial ones, the x's, y's, and z's, all by themselves, not involving t, those really are just the generalization of Pythagoras' theorem, maybe in a curved spatial geometry, those are the spatial distances. GTT, what is that doing? It's telling you how fast time flows. Now that's an entirely preposterous idea, how fast time flows, because time flows at 1 second per second. There's no other rate at which time will never flow at 2 seconds per second, okay? But the time that you experience tau can flow at different rates with respect to the time coordinate. The time coordinate is nothing physical, it's just something that we use as a convenience. So GTT, that component of the metric, tells you how fast time flows compared to the coordinate that everyone has agreed to use. And then the ones that mix space and time literally tell you how time and space can twist into each other. Now, we don't have any of that in the Minkowski metric. That's not going on. You might say, like, when is time and space going to twist into each other? When will I ever see a major Hollywood blockbuster in which that happens? Well,
stop into Raymore and Flanagan today and say goodnight to nagging headaches with the Sealy Posturepedic Collection. Engineered for superior support, Sealy Posturepedic was built to be the best for lasting comfort where you need it most. All night, every night. Shop Sealy Posturepedic today at Raymore and Flanagan. Convenient financing plans allow you to buy now and pay over time. Plus, receive free next-day mattress delivery and removal.
I'd do anything.
What are you doing?
Putting magic fairy dust on Murphy and Buzz so we can play together forever.
Oh. Hi, I've got a better idea. That doesn't involve glitter. Great. Let's go to PetSmart. Check out Hill Science Diet. It's formulated for long, healthier lives. And get it delivered with auto ship, so it never runs out. It just appears at your door, like magic, without the glitter. Thank you. Yeah. Anything for PetSmart. You. Anything for pets.
you have. Because time and space twist into each other when you are close to a rotating black hole. This is a famous image from Interstellar, right? The movie. This is the black hole, Gargantua. And all of the image here, all of the little filaments of light, were calculated numerically by using a metric tensor which had significant rotation, twisting of time and space into each other. It was so much work that Kip Thorne, Caltech Nobel Prize winner, who is also the executive producer and inspiration behind Interstellar, collaborated with the special effects folks here in the UK to write a paper. I mean, they also made a movie, but they wrote a paper, more importantly, in classical and quantum gravity, where they explained all the mathematical details that go into making this picture. And if it weren't for the components of the metric tensor that let time and space bend into each other, it couldn't have happened. I hope you enjoyed that little pop cultural interlude, because that's it. No more of that. Getting serious once again. Okay. So Einstein is taught that Riemann figured out how to capture the information you need to characterize a perfectly arbitrary curved geometry. Now you need to put it to work. How do you make money out of this metric tensor? Because what you care about is not the distance along a curve. What you care about is the curvature of space-time. What does that mean? Well, if Euclid says that you start with two initially parallel lines and they stay perfectly parallel, and Euclidean geometry is flat geometry, then curved geometry is not flat geometry. Curvature is all of the different ways in which those initially parallel lines can fail to be perfectly parallel forever. So we have a way of characterizing this called the Riemann tensor, much better than the metric tensor, because the metric tensor only has 2 Greek indices. A Riemann tensor has 4 Greek indices. That's twice as many. And the game that you play is, you tell me what point you start with, what line segment you start with, what direction your initially parallel lines go at. You ask the Riemann tensor the question, what happens to them as I extend those lines? And the Riemann tensor tells you how they twist around or converge or diverge or whatever. So the Riemann tensor is really capturing what you care about in the geometry, that is to say, its curvature. The g mu nu is the raw data, the metric tensor, but what you want is the Riemann tensor. So just to get this, in context here, we've seen secretly different kinds of tensors, different kinds of quantities that are geometric and have different numbers of components. A momentum in space-time, in ordinary Newtonian mechanics, momentum is a three-dimensional vector, but guess what? In space-time, it's four-dimensional because you have a time-like component as well. You've seen the metric tensor, 4 by 4, so 16 components. The Riemann tensor has 4 indices, so it is a 4 by 4 matrix of 4 by 4 matrices. And I swear if anyone says they see a typo in this, I'm going to smack them. Again, this is one of those slides you're not supposed to get any knowledge out of it. You're just supposed to be impressed and go, wow, there's a lot of Riemann tensor out there, okay? And if you're a graduate student in physics, in my day, you would calculate the Riemann tensor. These days, they have their fancy computers and everything, and they don't know what that's like. So this was a lot, so let me just capture what you're supposed to take away from this, okay? The geometry of space-time is what you need to talk about in general relativity. This is Einstein's insight. If gravity is a universal phenomenon, then it is not like electromagnetism or other forces. It is a feature of space-time itself. What feature is it? It's the geometry of space-time. He needed the math to describe that. He was taught it. It's Riemannian geometry or differential geometry. That can be arbitrarily complicated, but Riemann let us whittle it down to a little usable piece of information. How to calculate the length of every infinitesimal curve, and from that you can build up the geometry as a whole. That information in turn is captured in the metric tensor, 4 by 4 tensor in 4 space-time dimensions, and that tensor has a curvature characterized by the Riemann tensor. So in other words, the metric tensor and the Riemann tensor aren't completely separate. The whole point of the metric tensor is it tells you everything you need to know as long as you can extract it. So the Riemann tensor is defined in terms of the metric tensor. If you're a working general relativist, your day job is usually figuring out either the Riemann tensor from the metric tensor or some vice versa kind of version of that. The next question, if you're Einstein, is how are you going to use that technology to come up with a physical theory, a theory of...
Outdated IT systems in healthcare are a serious medical concern. Are you experiencing daily fatigue from help desk phone calls? Stiff fingers from stitching together servers and software solutions? Or headaches caused by complicated compliance processes and manual workarounds? You may have outdated print systemitis, sometimes known as "why is our PHI in a system as old as an Atari?" syndrome. Or print servers, a disease that plagues IT admins worldwide. You don't have to wake up every day dreading the pains caused by print servers. Vasion Print, formerly Printer Logic, provides instant relief. Vasion Print integrates easily into your existing systems to automate front and back-end print management. Customers also found it cured print blindness, enabling them to see data from every print job after just one implementation. Vasion Print is the #1 treatment for resource-intensive on-prem systems. Vasion Print can be used to protect PHI and sensitive data, create your own custom rules to automate compliance and reporting, and eliminate problems caused by print servers. Don't use if you're allergic to cloud-native serverless solutions or systems that just work. The most common side effects are feelings of euphoria, fewer compliance issues, and reduced help desk tickets. For free information, schedule a demo and discover the benefits of Vasion Print for yourself. Try a 30-day trial to see how Vasion Print can alleviate your print pains.
Gravity. Well, you knew what Newton did. Remember, this was not just showing off when we talked about this before. This is Newton's way of telling you the acceleration due to gravity, right? The acceleration depends on Newton's constant times the mass of the Earth or whatever it is causing the gravity divided by the distance between you and the Earth squared, the center of the Earth in this case. So Einstein needs to replace both sides of this equation. On the left side, the acceleration due to gravity, he needs to have some measure of the curvature of space-time. On the right-hand side, the source of gravity. For Newton, the source is the mass of the gravitating object. What's it going to be for Einstein in this relativistic context? You already know it's not just going to be the mass, because Einstein told you that E equals mc squared, which is a hint that energy and mass are somehow unified. They're somehow part of the same thing. So mass is not the primarily important thing that it was for Newton. In relativity, mass and energy and heat and momentum and strain and pressure, all of these things are somehow going to be sources for gravity. What we need, I should ask if anyone can guess. Do you know what we need? We need a tensor. And we have one. I didn't give you time to guess. Sorry about that. I didn't want to be shown up by someone actually guessing. So the energy momentum tensor is basically another 4x4 matrix that tells you all of those things. It's called T mu nu, and it encapsulates all of the different forms that energy and momentum and other related quantities can take. And once again, we can look at it component by component. There's a 0,0 component, or TT component, if you like. That tells you the energy, including the mass. That's what we usually think of as the amount of energy in the good old Newtonian sense. These diagonal components, Txx, Yy, Zz, that's the pressure. So we're thinking here not just of a single object like Newton would have thought of, we're thinking of maybe a fluid or a solid. So you take some little region of it and there's pressure in the x direction, the y direction, the z direction. Those different directions are the diagonal components of the energy momentum tensor. And then there are off-diagonal components which you can sometimes ignore, not always, but they tell you about how energy is changing and moving from place to place, the heat flow, the momentum, and so forth, okay? So all together, all the different ways that you can think about energy are bundled up in this tensor. This is definitely going to be something we're going to use as we construct the new equation for gravity that Einstein is looking for. We have the metric. The metric defines the Riemann tensor, which characterizes the curvature of space-time. Mass is a kind of energy, so we're beginning to see left-hand side and right-hand side come together. We want to replace Newton's equation, okay? There's an obvious guess that it's not going to last very long. On the left-hand side, acceleration maybe should be replaced by the curvature of space-time, which is, as we know, characterized by the Riemann tensor, r lambda rho mu nu. And the right-hand side of the equation, which has the mass in it in Newton's equation, should have the energy momentum tensor, T mu nu. So we have curvature of space-time on the left, stuff, energy, momentum, and mass, and so forth, on the right. It obviously doesn't work. I can just imagine Einstein going like, it was so close, and it didn't work. It doesn't work because the Riemann tensor is a 4x4 matrix of 4x4 matrices. The energy momentum tensor is a 4x4 matrix of numbers. They don't match up. They can't be proportional to each other. Fortunately, there were some very industrious Italians who read Riemann's paper back in the 19th century and figured out all sorts of things you can do to the Riemann tensor. Basically, you can distill it down. So you can contract, as they say, the Riemann tensor to make something called the Ricci tensor, after Professor Ricci. And the Ricci tensor only has 2 indices. And then you can actually contract that again to get something called the curvature scalar. So when Einstein is trying to think of what can he put on the left-hand side of his new equation for gravity, he has various ingredients to play with. He has the Riemann tensor, but also the Ricci tensor, and also the curvature scalar. Now you're instantly going to guess. I want to take the Ricci tensor, because it has 2 indices. I'm going to set it equal to the energy momentum tensor, which also has 2 indices. If you're guessing that, congratulations, you are just as smart as Albert Einstein, because he guessed that. It didn't work. It doesn't work because energy is not conserved in various other problematic things. But again, because he was Einstein, he worked harder and he came up with this thing. R mu nu minus 1/2 R g mu nu equals 8 pi g t mu nu. That is the correct generalization of Newton's equation to the relativistic context, and we now call this Einstein's equation. You saw it a few minutes ago, but now you perfectly understand it. But the point is, you see why even if your understanding is only 99%, not 100%, you see that it's not just showing off or egregious, right? Like these symbols have meaning. These mu's and nu's talk about directions in space-time. They will take on different values, 0, 1, 2, 3. R on the left and G on the left are different geometric quantities telling you about the curvature of space-time. T mu nu on the right is telling you about energy momentum. G is Newton's constant of gravity. 8 and pi you've met before. So if you get this far and you appreciate that now you have an equation, the next step, of course, just like for Newton's equation, is to solve the equation. What that means is, what you want to know is the metric on space-time. So the metric is what you need to actually calculate the force on a rocket ship or a planet or whatever, or a black hole, okay? The metric is implicit here because you use the metric to define the Riemann tensor and the Riemann tensor to define the Ricci tensor and the curvature scalar, but it's a little indirect. In fact, it's kind of like super duper indirect. So just to let you know, I've written out one component of the Riemann tensor in terms of the metric. Here it is. So in principle, you could say, all right, I'm going to be plucky. You assign your least favorite graduate student the job of trying very hard to solve this. And Einstein himself realized the level of complication, the number of mathematical operations you have to go through to go from metric to Riemann and back and forth and solve his equation. And he said this, no one's ever going to do this. I'm not going to do this, and I'm Einstein. So no one else is going to do this. Carl Schwarzschild went and did it. Schwarzschild is a fascinating story. He was an astronomer and mathematician by trade, but it was, remember, look at the dates on this. 1917. There was a war on, you might remember, right? World War I. And Schwarzschild, because he was good at math, was given the task of calculating ballistic trajectories for the Germans fighting the Russians on the Eastern Front. But they were, I don't know what the details were, but apparently there was shore leave or something. And it's not the Navy, so it's not shore leave, but he had some time off from fighting at the front, and he was allowed to go to Berlin, and he spent his time off listening to lectures by Einstein on relativity. It's a choice, you can't argue that. And Einstein gives his equations, and he says no one's going to solve them. Schwarzschild goes back to the front and he sits down and solves them. And so how can you possibly do this? Well, you make a lot of guesses. You make a lot of assumptions, right? You say that doesn't sound very sciencey. I'm going to use the German word. I'm going to call it an Ansatz. An Ansatz is a guess. And in this case, what Schwarzschild said is, look, I don't care about the general arbitrary solution to anything. I care about the Earth moving around the sun.
We have apprehended a dangerous experiment.
He escaped.
Tickets available now.
You sure that's a dog?
Yeah.
Rough. Agent Cobra Bubbles, I need to find out what kind of threat we're dealing with.
You can't take him.
What the? Disney's Lilo and Stitch. Rated PG, now playing only in theaters.
Why would anyone keep on running in this weather?
So I'm going to ignore, actually, the Earth and Jupiter and everything. I'm going to take the sun, put it in the middle of my coordinate system. I'm going to use spherical coordinates, just like we talked about. So rather than t, x, y, z, it's t, r, theta, phi, as you can see in the equation up here. And I'm going to assume all the off-diagonal elements are 0, and et cetera, et cetera. And I'm going to assume everything is static, nothing is vibrating. And then he actually whittled the problem down to something you could actually solve. And this expression here is the celebrated Schwarzschild metric. This is the exact metric for a perfectly spherical, empty space solution to Einstein's equation outside a star or planet or something like that. And Einstein himself saw it and was instantly impressed. That's memorable because Einstein was handed lots of papers, and he was not usually instantly impressed. He usually had a reason to disbelieve them. For Schwarzschild's solution, he was very, very happy. Now, from here, now you're cooking with gas. Now you can calculate the motion of the Earth around the sun, or more importantly, the motion of Mercury. You can calculate gravitational lensing and gravitational redshift and a whole bunch of other predictions. One of the reasons why Einstein so quickly became a celebrity is because his equation led to predictions which were tested and successful at them. Arthur Eddington led an expedition to look for the gravitational lensing of light during a solar eclipse. It is believed that he was less than perfectly rigorous with the data, but he got the answer that he knew he wanted to get. And Einstein was very happy. But I don't want to talk about that now. We were running out of time, so let me just talk about one fact that you can glean from this equation. I want to let you know that it's not just some symbols here. You can get something out of them. So remember, we have interpretations or meaning for these different components of the metric tensor, right? GTT is the rate at which time flows for an observer compared to the time coordinate, etc. And you look at this, and you look at GTT, it's the upper left-hand corner, right? 1 minus 2gm over r. R is the radial coordinate, g is Newton's constant, m is the mass of the thing. And you go, wait a minute, when r equals 2gm, this whole quantity equals 0. It's 1 minus 1. So time isn't flowing? Or something like that? What is going on at r equals 2gm? And then you look at the RR component, the next one down, diagonally, and it is, if the TT component was 0, this one is minus the reciprocal of 0, 1 over 0, which is infinity, and that's bad. So as soon as you write this down, you're like, there's something weird seems to be happening at r equals 2gm. So what did people do? Well, they said they calculated the value of r equals 2gm. So you know the mass of the sun, you know the radius of the sun. At what radius are we talking about here? And what you very quickly find is that the relevant value of r, which is now called the Schwarzschild radius, for obvious reasons, is much, much smaller than the actual radius of the sun. And this solution is only supposed to be valid outside the surface of the sun, not deep into the interior. So people said, and correctly, the fact that this metric seems to go haywire when r equals 2gm is not physically relevant for things like the sun, the earth, etc. It only refers to places where the solution is not supposed to be valid anyway. Some more imaginative astronomers said, yes, but what if the thing collapses? You can see a 3-hour biopic about one of them if you go to see Oppenheimer. Oppenheimer and his student Harlan Snyder solved not for the static case, but they allowed a sphere of mass to collapse. And they showed that it collapsed and went right beyond the Schwarzschild radius. So this could be relevant physically. What is it? You all know what it is. It's a black hole. Here's a picture of a black hole. Not the black hole, you know what I mean. It's the picture of the light going nearby a black hole. This is from the Event Horizon Telescope. But here, just to make it vivid, remember, what is G00, GTT? It's how fast time flows compared to the time coordinate. I'm plotting it now. 1 minus 2gm over r, so this is r in units of gm on the horizontal axis, and there's G00. And so you see that at r equals 2gm, this number goes to 0. So at that place, the rate of passage of time experienced is 0. From the point of view of an outside observer, we call that place the event horizon. It took decades of clever mathematical work. It wasn't really until the 50s that people figured out how to just change coordinates, and there wasn't a barrier that you hit at the event horizon. You could just go right through it if you wanted to. These coordinates aren't very good there, but coordinates are just human inventions. They're nothing very deep. And furthermore, there was work by people like Chandrasekhar and others that showed that these collapses can actually happen in the real world. And finally, they started saying in the 50s and 60s, maybe these black holes actually exist. Nowadays, of course, we take pictures of them. We give out Nobel Prizes like candy for people who are observing them in various ways. And the point of this is the last slide, which is that the reason why we care about these equations so much is because the equations are smarter than we are. Albert Einstein was pretty smart. He derived that equation that we show you here in the middle of the slide, but he never knew about black holes. He never fully understood gravitational waves. He was always somewhat uncomfortable with the idea of the Big Bang. The equations just sat back smugly and said, you'll figure it out eventually. And we're getting there. Same thing with Newton's equations or with Maxwell's equations or with Schrödinger's equation of quantum mechanics. We do some experiments locally here in our short, brief lifetimes. We make some leaps of imagination to distill all of this complex physical behavior down to this little concrete poem, and then we blithely extend it to circumstances we haven't even imagined seeing yet. And a good equation is going to teach us something that will go, yep, the equation knew it all along. Thank you.